welcome everybody. How are you doing? We enjoying the weather? And no? What? No, I am curious. Why are you not enjoying the weather? You don't like hot weather?
It's hard to breathe. I sweat. It's uncomfortable.
Okay. All right. That I will exercise that. It is tough to sweat. I am grateful for a change of season. That seems to kind of be upon us. Well, today is kind of either going to go very well or it's going to be embarrassing. Okay? Because we're going to try to do a lot of Ansys in real time. So if it works out, great. If it doesn't, you can walk through. Okay? But at least you've got me to walk you through some of the theory or some of the background on some of the material. Okay? Just in terms of announcements, there are a number of assignments and things forthcoming in this class. So the lab that you'll have is a combined lab post lab, and it's pretty in-depth, one shot. I need to post the actual assignment, but you will probably have a pretty good idea of what's expected if everything goes as you like it to. And you could go ahead and run the simulations and then hope that when you open it after you save it, it doesn't get corrupted. So you may also want to wait until I've got the actual lab. That'll be soon. And actually, the assignment is in these slides, which are available, so you really do have a pretty good idea. You don't have to wait. I should get that out on Saturday. I'm also hoping to get some feedback to you all for your preliminary outlines. And on Tuesday, no, it's Monday, the demo simulation is due. And that will again happen in the same document that you've already submitted. So it behooves me to, well, I mean, I can go into the version history and look at what you submitted with everyone, but I'm going to try to get feedback to everybody on your preliminary project outline in that document. And then you can see the rest of the assignments. We haven't talked too much about the PowerPoint and the video presentation. I think I mentioned it though. Essentially, you need to create a 2-minute video that has 1 minute of you lecturing and 1 minute of you promoting in some creative way the results or the analysis that you have. And the PowerPoint is essentially just that 1 minute lecture. This is all to do with the last day of class. There is a final exam in the class that is scheduled for May 12th, and I'm working to have a separate journal. Can't all fit in here, and it will be pen and paper. And I don't anticipate you needing a calculator or else. I'll visit as I write it. We'll see any notes. It really though should be conceptual, and you can even anticipate things directly from the labs. You may even see screenshots from the labs. Okay, so it's not worth a tremendous amount. It's worth 15% of the grade, and it's going to be, I hope, it'll be like a fun, commemorating experience, a reunion. Okay, that'll be like our first reunion. We had a lot of people in this room the first day. We'll have a lot of people in 2 separate rooms the last. Okay, any questions administratively? Yes, yeah.
In terms of the final exam, will it be more on like mechanical know-how of Ansys and MATLAB?
So you should be able to do a little bit of math. Okay, I wouldn't expect you to. I mean, you should know something about finite volume, finite elements. There might be something where be able to do finite difference by hand. Okay. And so I might give you, a simple difference or a forward or backward difference. Those things are reasonable. But I would, if you had to bring in a piece of paper, then you want to write it down. If I say you want to bring a piece of paper or not, you should be able to use them, and you should be able to do like a basic or modified whatever method that you use. That makes sense. You know something about boundary conditions. Professor Singer was writing this exam, we using a lot of boundary conditions. No slip, shear, mirror, right? And no shear is like a mirror symmetry. We had balancing, we had periodic, right? So there are a bunch of different boundary conditions that we've gone through, and we're going to go through still, especially when we get to mechanics. So that, I still need 3 hours, but I'm thinking it won't take 3 hours to do. But I thought about a lot of these answers. So we'll see how it works. All right, you're the first ones to have this experience. Any other questions? Yes, Josh.
Would you be able to give us previous exams or like some practice exams or something like that sort?
There's none, right? So I'm telling you what to study, right? I'm trying to tell you what to study. I'm trying not to, the first time I'm going to try not to be too picky. That's why I'll try to do. Typically, this class, if you have, you're actually able to get over 90%. And that's a hit. Typically, the average is it doesn't reflect meaning at curve, right? Like you'll have an average that's probably above 80%. So that means that I'm not going to reverse curve it. Right? That doesn't make any sense. So typically, the grades are broken down. 90 to whatever, 80 to whatever. Standard, like high school, right? So that's how it goes. But we'll see. Everything can change. It also depends on we have 3 different people grading things. So if we do have to institute a curve, we will. All right. So today we're going to talk about flow and drag on a sphere. So I ask you, why would I spend, and hopefully not waste, an hour of your time to talk about flow and drag on a sphere? Any ideas? This is not like a theological question of why are you here, where are you going, but I'm asking you that in the context of why are we talking about drag on a sphere? You raising your hand, kind of. So if you want to guess.
So far, we've really only done dimensional simulations, and those simulations with a cylinder can be done in 2D. It's the same depth of the sphere, depending on where you are in the z-axis. It's a different velocity profile.
Yeah. Hate to disappoint you, we're still going to be doing an axisymmetric for our simulations, but we will talk about the 3D nature of flows, about a sphere and how we are not capturing some of the dynamics and the fluid mechanics that you would see in a 3D experiment. Okay, so good. So like we're extending our dimensionality. Okay, that's great. I like that. What else? Other ideas? Why would we spend time on this? Sure.
We need to forward track.
Yeah, right. I mean, if you're going to say, hey, you know, I'm interested in like the terminal velocity of this object falling down in the sky, sphere's not a bad place to start, right? Yeah. So there's truth to that. That's true. I mean, Professor Singer says you can model many things with strings. I agree. Mechanical things. In fluid dynamics, you can model many things with spheres. Okay. So it's not considered accurate, but you could do that. Good. Any other thoughts? Yes.
Related to the last point, I think the sphere is also like one of the few cases where you have an exact solution, and it's easy to compare.
All right, good, right? So that's exactly what I was going to essentially say. Ground truth, right? We talk, and convergence will definitely be on the final exam. We talk a lot about convergence, right? And there are two ways that we've established to establish convergence. One is the value doesn't change as I make time step or mesh or some effect. Whatever my in value of interest is doesn't change as I manipulate the parameters of my simulation. That's when I know it's going to converge, at least on a numerical solution. Could be right, could be wrong. The other way is, yes, there are experiments that are out there. We can make comparisons to the Stokes flow about a sphere. It's a laminar case, it's creeping flow, which we're going to do in a few minutes. So we have the ability to think of these experiments in computational fluid dynamics as ground truth. And we'll see how frustrated I am. I did a simulation this morning, and I got one value, and then I went back and I changed one thing, and I got another value. The first value was correct, the second value, I don't know why. Right? So this is one of those things that you're starting to see it too. And it's also a case for moving towards scripts, right? We're doing a lot in the GUI world, but in the future, you may see us move to, well, in your future careers, I don't think this class will change it, but if you take future classes in finite element, finite volume, computational simulations, you're probably going to see yourself doing more coding and less pointing. Okay? But I think that Ansys and COMSOL are very, very good at being able to bring us to solutions with a bunch of clicks. And once you've got it, as Chris Lars showed us, you can use APL to automate those processes. Anyway, so we're going to attempt to go through different regimes and some overviews about flow over a sphere. There are different regimes for the flows. What do you think creeping means? That means that we're stopping the sphere fluid. But what do you think that means? Really slow. Okay. And then there's you can speed things up a little bit. You can get to some moderate vortex shedding, and then you can get to turbulence. And the Reynolds number is going to determine a great deal of where we're going to end up in these different regimes. Now, we've talked about the drag coefficient before, and you know that if you've got some kind of 2D or 3D projection, you can think about either the frontal cross-sectional area that's being exposed, the A over here, or you can think of the wetted area as you might think of an airfoil instead, so the span times the length. Or a surfboard, okay, where you think of, okay, I've got this big area that's in contact with the water, and that's my wetted area. So you got to be careful when you calculate the drag force, what the table you're looking at is essentially saying the area of interest might be. Now, we can rewrite CD as we see there, and for Stokes flow, okay, Okay, so for a Reynolds number much, much less than 1, you can say that the drag force is this analytical expression. So this is the diameter, this is the velocity, the free stream velocity, the dynamic viscosity, then the coefficient at 3 pi. Now, you can also look at graphs like this that are going to tell us what the drag coefficient is in different regimes, so at different Reynolds numbers. And it's kind of interesting that it actually at low, at creeping flow, the drag coefficient goes down. And it behaves like this, okay? And actually the coefficient of drag, and I think it's on a future slide, but for Stokes' law, here, the CD is actually 24 over the Reynolds number. That's what this, and we could manipulate it right now if we want. I'm not going to. I think I can do it later. But you see, FD equals 3 pi mu CD. FD equals 1 half rho v squared CD. Okay, so we can essentially calculate these out. Notice it's kind of interesting that the drag coefficient actually drops at this fourth regime. This drop, okay, or this kind of interesting thing is called the drag crisis. Okay? It's like, I don't know, the stock market has a crisis, your flow biosphere can have a crisis too. And then it kind of comes up. Now, so there's almost like a step change from here to here, and you see that it's kind of flat, right? So if you're not sure what to use for your value on a sphere, and you know that it's, a modest or kind of turbulent actually flow, so Reynolds number greater than 1,000, put in 0.5. That's not a bad guess, or put in maybe 0.2. Okay, that gives you a ballpark for what the drag force might be. So this is nice, and this of course is experimentally verified. You can see there's a difference between the behavior when you have a smooth or a rough surface on a sphere, right? So the transition to turbulence happens a little bit sooner, right? We talked about this in the past too. When you have a pristine, nice, steady flow, everything's smooth, there's no jumping or shaking of the ground or your apparatus, you can delay the onset of turbulence. And that's what you see as you go to this, you progress into this supercritical separated flow, okay, with a turbulent boundary layer, that if it's smooth, you're going to experience the crisis at a higher Reynolds. Well, I've got this here. The other thing, and this is relevant to the assignment you'll do, is that okay, so you see here that you have this downward, this concave up portion here, and you see that the drag force for creeping flow is proportional to velocity. And so that's actually reflected in this curvature. Whereas when you get to turbulent flow, the CD flattens out. Well, this means this is a constant CD is, the area is a constant, the density is not changing much. So it actually means that the drag force, even though this is flat here on the CD curve, the drag force is proportional to velocity squared. So if you were to see this graph on an exam, you'd be like, oh yeah, I remember now, if I have a turbulent flow about a sphere, be just proportional to the velocity. Okay, now even in these different regimes, within these different regimes, you can have slightly different behavior. And so there are all these links if you want to learn more about this. Do it. This is good material for a Friday night when you're looking for something to do. So when you have very low Reynolds number with creeping flow, the streamlines, they come pretty close to recombining, not so far from the surface here. So there's maybe a little bit of detachment. It's not completely symmetric, but it's pretty close to symmetric. Okay? And you'll see that when we do the simulation. As you get a little bit faster, so as the Reynolds number increases, then you can begin to see, maybe slight disagreement. So the accuracy is maybe within 10% of the COMSOL approximation, and so you're starting to push the edges. Okay, it's still creeping flow. Okay, but we're getting closer to the onset of turbulence. Right, that's what it means. Okay, so I don't think I've had a chance to really tell you about what I did as a graduate student, but here you go. Whether you like it or not. For a not too long period of time, a few years of my life, I got very interested in understanding how to get rid of bubbles from polymer solutions. Okay? Bubbles, some of them, many of them, are close to spheres. So I was looking at relationships for how the bubbles would flow in molds. Okay, so we were attempting to mold devices that had micro or nano features on them, and we wanted to mold them in a way that would not have bubbles. Right? So what are some typical ways to make sure that polymer parts do not have bubbles? You pick up your plastic plate or your toothbrush, right? And you're like, oh, that's a really nice piece of plastic. I'm glad it doesn't have any bubbles. How'd they do that? Yes?
I guess one basic method is to just, when you're injecting the polymer into the mold, use relatively high amount of pressure.
Yes. Okay? So that's a good way to do things, right? Is to use pressure, and what happens is that pressure squishes the bubbles, and inside the bubble, at the bubble wall, that high pressure leads to a gradient in concentration of air. So imagine a bubble, and now you're pushing it, you're squishing the liquid that it's in. The surrounding liquid has air dissolved in it too. Okay? But now that you've squished and you've compressed the bubble, that amount by Henry's law, the amount of pressure, the amount of concentrated air dissolved just in the interface of the wall is much higher than the surrounding liquid. Okay? The concentration of air in that wall. And so what you have is a gradient, and so the air will go from the inside of the bubble through the walls into the surrounding solution. So you do know you've heard of dissolved oxygen, for example, right? And you know what happens when you heat up and shake a soda. Okay? What happens is you're essentially taking that dissolved carbon dioxide, that's oxygen, right? Dissolved carbon dioxide, and you've given it nucleation sites so that it can explode. Okay? And temperature has an effect. So cold means you can hold more nutrients. Hot means it wants to get rid of it. So that's maybe a little bit opposite of what you're thinking with injection molding. Because when you heat stuff up, you're expanding things, right? But what you're doing is you're compressing living daylights up. So I just do injection molding for my polymer parts? Okay, so when do you use injection molding? Why don't you do injection molding when you go to the machine shop? You're like making your RFR car, making your rocket. It's like, hey, I heard that I should just use injection molding because it's really good at making parts out of plastics. Why don't you do it? Yes?
Like you need a lot of equipment and material.
Yeah, the capital cost is, woo, and you're not going to make one, right? Injection molding is typically used for making millions, okay? And you got to spend a lot of money on getting that die, getting that mold made. It's extremely expensive. So you only get payback if you make a lot of parts. Often you're better off doing machining. So let's say that you're a startup company making chips, and you're thinking you're going to make like these little chips of plastic with channels and stuff and microfluidics. You want to spend all the money to make a die, and on top of this is not a normal plastic. It is polymer, but it's silicone. And people do injection molding with silicone, and there's reaction injection molding. There's all kinds of fun stuff. But if you're only making a few parts, we're saying, hey, this is kind of for a medium flow production. So from this figure, and from what you read there, what did I do instead? What's that, Cameron? Yeah. So I'm sitting around at my desk, and I've got this liquid, and I've got a mold, and it's here, and I'm like, dude, I can't get these bubbles out. Like shaking it, doing all this stuff, and the guy that's not in my lab right behind me says, why don't you just spin it? I'm like, spin it. Okay, so let's think about that. So you spin. Let's say there's a bubble in the mold section. And this is the axis of rotation. Okay? So there's a bubble here. What is that bubble going to want to do? Okay, good. So there's gravity theoretically downward, right? Pointing downward. And so the bubble would want to hit the ceiling, right? Okay. Now, if I start spinning, which way does my gravitational vector now start going? Okay, so yes, you still, okay, so it depends on which side you're on, right? So, yes, the gravitational vector is going to start off like this, right? And then gradually, at least if I'm on this side, right, it's going to move more or less like that, right? So, now, which way are the bubbles going to go? Okay, again, left and right is hard here because I don't know which side of the board you're on. Right? So which way do you think it's going to go? Okay, so who says outward? Who says inward? Yeah, okay, inwards have it, okay? So what happens is, yes, you've essentially got this gravitational field now that's acting radially outward, and the bubbles, they go against gravity, right? You've seen that, right? Now, if I had lead pellets in there, right, then they would go out, okay, because buoyancy is going to be working in the opposite direction. But because the bubbles have such low density relative to the liquids, right, they move inward. Okay, so I spent time looking at simple things like, okay, what's the drag on the bubble? What's the buoyant force on the bubble? Okay, how fast is it going to move? As the gravitational field changes, going with omega squared r squared, or omega squared r, pressure is omega squared r squared. The gravity is less closer to the center. So are the bubbles going to go at a constant speed? No, they actually slow down as they get close to the middle. But the pressure is also less there. So the pressure means that the bubbles can expand, right? So it's actually kind of fun and interesting, right? And so I created models to describe this. One of the things that's interesting though is that bubbles can travel more quickly than solids. Okay. Why is this? Well, I know a few weeks ago, or a couple weeks ago, we were talking about how you have slip meniscus, right, between the ground and your foot, and like, you have the no slip condition on the bottom of your foot and the no slip condition on the ground and stuff. But anyway, what's actually happening at that air-liquid interface is it's actually slipping. Okay? So the liquid can slip along, and there's this Hadamard-Brzezinski relationship. This all looks exactamente like what we just talked about when we said, hey, this slopes slow. But then there's this correction term. And what it says is you look at the viscosity of the fluid and you look at the viscosity of the bubble material. Okay? And as you can imagine, this viscosity of the fluid is much higher than the viscosity of the bubble material. So then what happens is that these guys are insignificant, these guys are pretty significant, and you get a 2/3 factor. So you actually cut down your drag by quite a bit, by like 33%. Okay? So bubbles, small bubbles, okay, because that's the other thing that can happen is you have large bubbles that don't look like spheres anymore. But the small bubbles, for a given size, actually have less drag on them. Okay, so then here you go. You've got an estimate for the drag for small bubbles. And like I said, you also have diffusion happening. And diffusion is pressure dependent. So what essentially I would do in simulation is I seed a bunch of bubbles into the device, all right, and say, hey, this is where it's starting. How long is it going to take to get to this liquid air interface, right? Because the bubble is going to go this direction, if we're spinning now about this. And so how long does it take to get to the liquid air interface? And if it's a very large bubble, then it goes very quickly to the liquid air interface. If it's a very, very small bubble, because of something called the Laplace-Young relationship, because when you have a very tight radius, you have a lot of curvature, you actually have a lot of internal pressure. Really small bubbles just dissolve into solution. Okay? So, like, you won't find in an atmospheric pressure, you're not going to find, I'd say with a microscope, you're not going to find like a 10 micrometer bubble in a solution that's at atmospheric conditions that has pretty much regular concentration of dissolved air. Okay? Because it's unstable. It actually will collapse and dissolve into solution. So the bubbles that are the trickiest to get rid of are not the very large bubbles, are not the very small bubbles. They're these bubbles of a critical size, the medium-sized bubbles. And what's happening is these bubbles are moving along, and as they're moving along, they're changing their shape, and they're diffusing, and they're getting smaller, and they dissolve right when they get to the liquid air interface. Those are the killer ones. Those are the bubbles of the critical size. Okay. Anyway, if you want, you can read about it. It's not that interesting. Well, it is interesting. I thought it's very important. Okay, I'm very biased. But anyway, so we did some things there, but I wanted to show you the experiment that we did, or part of one of the experiments. So you see, this is a cylinder with a bunch of bubbles in liquid, and it's actually whipping out to the outskirts. And then this is 5 seconds later. You see a lot of there's still some specks in there, but a lot of bubbles are gone. And then you zoom in and look. These are the bubbles taking 1 shot per revolution, more or less. So we have a little bit of drag, because it's accelerating, right? So now it's reached steady state speed. So you see those bubbles are moving along. It was beautiful. It was beautiful. One of the reasons why they let you graduate, right? You have to do something to graduate. Otherwise, you're just in graduate school forever. Okay, so yes, that is an application of Stokes' law of Gauss. So now you say, oh, you asked us why are we studying this? I guess part of the reason is also I like bubbles. All right. So now, outside of that regime of creeping flow, you start to get into the donut regime. Okay. So you actually start to shed these vortices, okay, and you have these like little closed circulations happening behind the sphere. And as you get a little bit further along these little circulations can actually move back and forth. I've never seen this. I'm sure there are YouTube videos out there that have this behavior. I'm also pretending sure that it's very hard to replicate this because you've got to have everything just right. Okay. And then once you get to thousands, you start to see the shedding of ring vortices. And then finally you get, or actually maybe not finally, you start to see a lot of wake and turbulence. And then, yes, and then you can get to a drop as well, and then another bit of turbulence. You know, it's interesting that for these types of flows, people have used, when they're looking at how fish swim, right? Because they shed vortices. So people have looked at analogous systems with spheres, or cylinders actually, and tried to get the same type of vortices. And if you can have the same flow, and you can measure the force on the object that's inducing it, you can say that drag is like the thrust. Does that make any sense? So imagine that you have a fish swimming along, and it sheds a certain set of vortices. You see a certain flow pattern. You can't calculate, I mean, you can say, hey fish, how much force do you feel, right? So you could do something like that. But what people have done is to say, hey, look, those vortex shedding patterns are very similar to what I see when I put cylinders in a flow. And I can measure the force on a cylinder that's suspended in a flow, and so I can approximate what the thrust, okay, that drag would be now equal to the thrust. I digress. I'm just stalling because I really don't want to do the simulation. Alright? But we're going to get it. It'll be fun. So, one other dimensionless number that people will reference is called the Struhel number. Okay? And then you also, yeah, there's different, I can't remember the other parameter that people discuss, but this Struhel number has the frequency and has the length, okay, and has velocity, right? So this is the diameter sphere for the L and the flow velocity. So if you start using higher Reynolds numbers, you get an instability with a Struhel number of, let's say, 0.2. You can then begin to calculate, right, rearrange the Struhel number, so that purple stuff on the right, and you can get an idea of what the shedding frequency of the vortices is. So this is one of those cases where, once again, just like the Reynolds number is a dimensionless number that teaches us about the fluid flow, the Struhel number is another dimensionless number that also helps us characterize the flow. And then you have a whole host of different vortex shedding patterns. I mean, they're kind of fun, some of these names. You have the omega-shaped vortex. You have the periodic vortex shape. You have the no periodic vortex shape. You have the vortex loop. You have the vortex fixed, the fixed vortex ring. So again, to get all of these different regimes is an extremely tedious and difficult process. And then after we're going critical, okay? And I guess you could say, okay, this diameter is like a basketball, and this is 15 feet per second. So we hit this drag crisis, and we see a drop in the drag force, like we see here, right? And then I see it come back up. Okay. So here's some takeaways. Dependence on the Reynolds number, yes. We can use a coefficient of drag, so we don't have to run any simulations. If you can avoid them, please. All right. There are multiple regimes of flow, and you have a drag crisis. Okay. And you can also begin to see that there's an effect due to roughness and spinning also. So some of you will attempt to look at things with a Magnus effect. All right. So normally, when you have a ball that is not rotating, it's a symmetric object, just like a symmetric airfoil, like a NACA 012 or something. That's symmetric, right? We will do asymmetric. 2412 is one of them that's asymmetric. But if you have you expect to have drag but no lift, unless, of course, you pitch. You change the angle of attack. So the same thing is true with a ball. You should have only drag. And drag means it's a force that is acting opposite to the flow, or acting opposite to the travel of the object, whichever way, and it's essentially completely aligned with the free stream velocity, moving in the opposite direction. It's parallel. But if you start spinning the object, the ball, or whatever, the cylinder, whatever it might be, okay, then you can induce additional difference in the speed of the fluid about that object, and you can induce lift. Okay? So golf balls are one case where they're hit, they spin quite a bit, and that means that they don't follow a straight parabolic arc of travel, but I don't golf, but they go up, and then they go over, and they go farther. Magnus effect. So some of you will work on doing that. You can prescribe a surface velocity, right? So just like you said, oh, hey, no slip, you can also prescribe a velocity of the fluid at that boundary around an object and fluid. And that you can use to approximate the Magnus effect. Okay. So, creeping flow. Okay. The point of this here, all right, is to say, here is Navier-Stokes. This term over here, this inertia term, this is where the total derivative or the material derivative resides, and then you have a divergence times the nabla times the velocity. You forget about this whole term. Okay, we're going to say in creeping flow, and this is an assumption I used, even though I knew that the bubbles were changing their speed, I would assume that they got to that new speed instantaneously, and I would get rid of the acceleration. And you can calculate this out. You can say, oh, I believe I will have changed my speed over this period of time with this density or this size object. Is that a significant amount of force in my system? And if it's not, then you can forget about it. Okay? So one thing that I don't know how to do in Ansys, but I do know how to do in COMSOL is run the simulation for creeping flow, because it has an option in COMSOL that ignores this term. Okay? So for Reynolds number much less than 1, we can ignore the inertia terms. And so the creeping flow, and if we ignore gravity, the creeping flow is just going to be the change in pressure, or the gradient of pressure, is equal to the mu times the Laplacian of the velocity. Okay, so this is essentially the PDE that COMSOL will solve. And you can look at details of how this works, but it's using second order elements for velocity, and it's using first order elements for the pressure. Remember, what technique does COMSOL use for fluid dynamics? Finite element. What technique does Fluent use for fluid dynamics? Finite volume. Right. So we're also looking at essentially two different approaches numerically that the computer is going to use to solve the problem. So here's our setup, and I'm going to open up COMSOL. What we're going to attempt to do is have a axisymmetric setup with a sphere. Okay, this is the axisymmetric this is the axis of symmetry right here. We're going to bring in fluid, okay, like this, and we'll have an outlet down here, and we'll say it has a radius of 50 microns, and we'll have some distance here. The drag force, if you calculate this all out using that 3 pi mu v formula, should come out to be about 0.9 nanometers. So let's see how it goes. The viscosity of the water is going to be 0.001 Pascal second, or 1 millipascal second. Okay, so I have, of course, I opened up Ansys, and I opened up So some aspects of COMSOL are very similar to, or at least the user interface is very similar to what you've been seeing with Ansys. And now you can say, well, you have been introduced to it at least. So what we're going to do is we're going to say we're doing a 2D axisymmetric problem. We're going to use, so if you come over here, it has recently used because I recently tried this morning to make sure it still worked. We're going to use single phase flow. So this is a case where we have completely rigid boundaries. So there's not going to be not modeling solid, and there's only one phase of material, which is the water. So we'll go ahead and introduce this. We'll add it, okay, and it gives us these parameters. So COMSOL is a little bit more, at least it helps you feel that you're more connected to the partial differential equations. In fact, you can just plug in the partial differential equations that you want in the weak form, in the general form, and different formats that they have. I guess I won't. Oh, I can show you that, because if you go down here, there's this whole math section. So if you want, there's a PDE interface, so you can have the general form, or you can have like what's called a coefficient form for PDE. So different coefficients correspond to different parts of standard PDEs. Okay, but we're not going to do that right now. So now we're going to go to the study. We're going to use stationary. That's the same thing as steady state, and we'll go ahead and click done. So now, this is interesting that it's like not, there, now it's showing. It just made me feel better to see the bottom. Okay, so here we're going to change our units to micrometers, like that. And we'll go ahead and put in a circle. Okay. Or maybe you'll put in the box first. I don't know, we'll see. We'll just put in a circle. And we're going to say that the radius is 50 micrometers, and we're going to build it. Okay, so there's a circle. And then we're going to build a rectangle, and we'll say that this is going to have a width of 250 microns, and the height will be like 1,000, so like 1 millimeter. And then we will put this, we'll put it at like minus 700. I have to see, maybe this is going to be wrong. Okay, this looks like it might be wrong. Hold on. No, that's actually not that bad. Okay, so that's pretty good. Okay, and then what we do is we perform a Boolean operation. So we're going to do a difference. And we're going to say, okay, I want this domain, but I want to take out that little domain. And so I build all the objects, and I'm left with something that looks, okay, good. Even though I just don't remember which mouse button does which. When you do Ansys, they're different. Okay, so that's the geometry. For the material, we'll come over here, and needs, it says entity needs a material. So we'll use the built-in one for water, liquid here. So now you can see it's only using dynamic viscosity and density, and it doesn't tell us what the values are, okay? Because it's a function of temperature. But it should be 0.001 Pascal seconds, at least at regular temperature, and it should be 1,000 kilograms per meter cubed for the density. Okay, now let's see here. The axis of symmetry in COMSOL is the vertical one, as opposed to the horizontal one in Ansys. And this wall, all right, we are going to, you see that it's being applied to this section, and this section. So this wall is going to have a no slip condition on it right here, but out here that's not what we want, and here was not what we want, and here's not what we want. What's happening here? This is essentially on an axis of symmetry. You have a mirrored boundary condition. Mirrored boundary condition meaning, hey, a fluid particle just really close on one side is going to be doing the same thing as the fluid particle on the other side, okay? And that is the same thing as saying no here. Right? So, but it's an axis of symmetry, so we don't have to worry about it. So what are we going to do? We're going to come over here. You can right click or you can go up to the top. We're going to add an inlet at the top. Right, so this is all looking kind of familiar-ish, right? So that's an inlet. We will go ahead and we'll add a, and we'll prescribe a normal inflow velocity. Okay, so this is supposed to be 1 millimeter per second. Okay, so it has the units already there. So I just got to put in 0.0001. And then we will define an outlet, which will be similar to what we do in the Ansys world. Okay, and you'll see that, oh, look, it's very similar. 0 Pascal for the pressure. Okay, and then out here, okay, so I'm just checking to make sure that we're okay with things. We have this with the no slip condition, symmetry, outlet, inlet. Okay, we gotta put a no shear condition on that outer one. So where did I lose it? Okay, so here for this flow, I can put in open boundary if I want, or symmetry would probably do the same. Actually, I don't remember which one I used. Let's go with symmetry, and if it doesn't work, it's my fault. Okay, now mesh. I'm just going to go ahead and use the default. That's not great. It's not horrible, but it's not bad. Okay, and we can close this, and we can zoom in a little bit. You know, you can get a good idea of what's going on here. Ooh, too much. Yeah. Okay, like this. All right. It's a stationary. Okay, so this seems to make some sense, although I'm a little. Let's see. I guess this flow is a little interesting here. I wonder. Let's just see if I use open boundary instead. If I get rid of this one, and I use open boundary, I wonder if it changes things. And then we come over here. Oh, I had to select it. Great. And mesh is still all there. We'll go ahead and run. Okay, so that does change things a little bit. What you see there is that the fluid can just kind of come out. Let's see what the drag coefficient ends up being. Open boundary is not horrible, but I think I do want to just leave it with symmetry instead. Okay. And we're good. So we come over here and we run. All right, so we've run this simulation. Now, what we need to do is come in here and look for a derived value. Okay, and we're going to, it's a little trickier to do the drag calculation, but not horrible. So we're going to do line integration, and we're going to do it about this surface, okay, or this curve right in there. Okay, you see that? Okay, because that's how we would measure the drag force. And then we put in an expression. What do we want? So you had to know, you had to play around a little bit here. We are going to go under creeping flow. We're going to look under auxiliary variables, and then we're going to come down and we're going to look at traction, and we're going to look at traction in the Z. So Z is the vertical direction, okay, and that's what we were looking for the drag force. So we put this in there, and then we just say evaluate. Okay. And what do we get? This is the moment where I'm a little nervous. Okay, so we got 1.4, okay, times 10 to the minus 9. That seems a little high to me. Why? Because it's not completely off. Right? Okay, but I'm looking for 0.9. So, you know, it's not horrible, but it's not great. So what happens if we do a couple things here? Let's come back, and let's say instead of using symmetry, just want to make sure I use the right one. Yeah, this 0.001 meters per second. If I disable this one, and then I add the open boundary, and put this here instead, and then I calculate it. Okay, and then I look at my line interval, and I evaluate it. Okay, I like this one a little bit better. Okay, so this is 0.89, okay, times 10 to the 9, 10 to the minus 9. Okay, so that one's a little bit closer. We're still not quite there, right? We're still not matching the theory. So what can I do? I could do a whole kind of convergence study. I could increase the mesh, right? I could increase the number of mesh elements, right? And I can also look at increasing the height, okay, the width of this. So for example, in this situation, I can come back all the way to the geometry, and I can change my rectangle, and I say, hey, I want to know if I make it 350 there instead. I build all the objects, and then I run my study. Look how fast that was. Right? And then I come over here, I do evaluate. Okay. Now, okay, I'm getting another value, right? So let me just clear this all. I want to be clear. Before I got like 0.88, like that's the one that I got. But let me just clear this whole thing, and I'm going to do an evaluation. Okay, so now I'm on the other side, right? I'm at one. That's close to. So 1 times the 9, minus 9. Right? So you see, this is not going to necessarily get me exactly the value I want, okay, but it's getting me close, and that's to be expected with multiphysics simulations. If I come over here and so right now I have normal element size, I could do like extra fine, okay, and see what kind of effect that has. So once again, I can run it, okay, and then I can look at the line interval, okay, and I got I think I got 1.04. Let me see. I can't remember which is which. Okay, 1.04. All right. So wait, that didn't help me get where I wanted to be. Right. But once again, I might converge on a value. Okay, that is like 1.03 or 1.02. Right. It's in the same. It's on the right order of magnitude for what the analytical solution is. Good. Okay. So that's COMSOL. And you can see that arguably that's a little bit faster in some respects than what we're about to do with Ansys. Okay, so with Ansys, we're going to do the same problem. Okay, and these are some notes that I can remember. We'll see how well we do, okay, with this. We're also going to do a more careful job with the mesh about that. So we're going to use layers, we're going to use inflation. So we're going to try a few different things, and we're also going to set it up so that it can be parameterized, so that you could have your table of design points here. So spoiler alert, right? What you're going to see is that as I change that before was that width of the domain, okay, but here's going to be the height of the domain. I also affect, as you just saw, the drag forces I measure. And I am actually getting kind of close to the values that I just showed, that 1.04, 1.03, right, in Ansys. Let's see if we won't be able to run all these simulations, all right? We'll be able to run one simulation, and then for your homework, you'll be able to use the parameterized model to be able to change this height. Why would you do this? Because you want to show convergence. Your assignment, not this checkpoint, right? This checkpoint is just a demo simulation. But your next checkpoint is going to be showing some type of convergence. So for that, you're going to want to change the domain, change the time step, do something that gives us an idea that we can trust the solution that we have at hand. Okay. All right, let's see if we can do this. So, we're gonna bring in Fluent. Oh wait, what in the? This is interesting. I don't want to kill everything. I like seeing things, but I'm nervous now. All right. I bring in Fluent, and we are going to be using a 2D geometry. Okay, so the analysis type will be 2D. So the plus side is that the font, I think, is a lot bigger than it normally is. The downside is I'm not quite sure why it's doing that, and like it's just kind of messed up things a little bit. Okay, so we're going to use space claim. And while this is coming up, I'll just go back over here and review. So we're going to have this 100 micron. When we say 100 micron, usually people mean diameter, right? So that means it's a 50 micron radius. And circle, but it's really a sphere. We're going to have a total length of 1,000 microns, and it's going to be offset from the inlet 200 microns. Okay. The height of this is going to be 200 microns. It's not on this, but it's going to be 200 microns as well. But it's going to be something that we can vary. Okay. But the initial starting will be 200. Okay. So let's see how space claim doing. Space claim. All right, good. There you are, space claim. All right, so now we click here on the Z, and we click here that we want to do on the XY plane, and we come over here. Okay. Before we get into the actual placing of a rectangle and circle, we can come over to the units, and we're going to use micrometers. Okay, for this one. So I'll go ahead and I'll put a circle right here, and I'll put 50, enter. Okay, and so that has made a nice big circle here. And then for our rectangle, we can come up over here, and we said it would be 1,000 horizontal. And we'll start with it being 200 in this direction. And we'll come over here and we'll click on the dimension. So we're going to put this inlet about 200, double click on it, 200 micrometers that way. Okay. And I'm going to control. I'm going to make sure that this is still 800 this way, so I'm going to do another dimension. Okay, so it didn't keep it, so I'll do that, then I'll double click, and then we'll put 800 this way. And I'm going to go ahead and, yeah, I can say this is going to be 200. I mean, it's already there, so I'll just leave it like that. But we got to do a little trimming. So you can come over to this trim tool over here, trim away, or hit T, and you're going to trim away there, and trim away there. So now we're just left with the domain where the fluid's going to be going, and we're going to have a no slip condition on that. You can come over here and hit End Sketch, Editing, and at this point you've got one surface, and that's nice. This is a little bit confusing. So what we want to be able to do is we want to be able to parameterize the height of this domain, right? That's like the width of the domain in COMSOL. So to do that, you click on Move, you click on this top, you click on this green. This is all left click. You left click on this little dimension ruler thing. And then you click on this base over here. And then you click on this P. And now you've parameterized it. Okay? Fun. When I get my act together, we might start using discovery instead of space claim. For now, space claim it is. All right, so we're gonna close this, and we should be good with a parameter that will appear in the workbench. Woohoo! All right, so if you double click on this, look, there's our DP0, okay, 200 microns, we're in business. Close that. Let's go ahead and get ready for some fun in the meshing application. Okay, so here we're going to define the inlet, outlet, no slip condition, axis of symmetry, all right? And there are some, for Fluent, there are 3 kind of reserved names. You already know about inlet and outlet. The third reserved name is axis. Okay, so if you name one axis, it knows that's going to be your axis of symmetry. So we're just waiting very patiently. Uh-oh, maybe I wasn't patient. Okay, great. It looks like it's here. So one thing you might want to do, or I suggest you do, is that mine is now set for micrometers. Okay, but if the first time you do this, it's probably not going to be. So you just come over here and you do that. You come over to geometry to check that you only have one surface. That's good. Okay, and then what we're going to do is go ahead and name some reserved or special spots. So I clicked on that left one. Actually, did I click on it? Yeah, click on it. I hit N. This is the selection name. So I'm going to do inlet, enter. I'm going to do this, and then shift. Actually, I think control is better. This. What's going on? That. Why? Uh-oh. That's not good. Nope. Why is it doing that? Okay, so inlet is fine. Okay, now it's fine. I don't know why it wasn't fine. Okay, yeah, I got them both selected. Hit N. This is axis. Okay, so now axis. Boom, that's good. It's red. Okay, this is going to be the outlet. N, outlet. Okay. We can call this, if we want, the outer mirror. Okay. And we can call this one the inner edge, like that. Okay. It's time to do some meshing. So if we do meshing like it is, we generate it, it's going to look a little lame. Okay. Not super cool. All right, so we're going to do a few things. One is we're going to come in here, and we are going to change the size of the mesh. Okay. So the default size is too large, so we're going to use 5 microns. Okay. And then the other thing we're going to do. Oops, I didn't want to do that last. Oh, I really didn't want to do that either. Okay. Okay. All right. Okay, the other thing we're going to do is we're going to change the mesh to use a triangular. So we do selection on this surface and hit apply, and then we do a triangle mesh like this. And so that means that this will be triangular. So we look at it, if we generate it for fun. Okay. We now see that our mesh is progressing nicely. It's starting to look like it could capture interesting behavior. And then we're going to inflate and break this into different regions around this inner circle. So we're going to go ahead and insert a sizing, and I can do, it is on this we can do it on the name selection if we want. Okay. And we can do it on the inner edge. And for the sizing, okay, we can put in something like 1. Okay, so that's going to be really small. So now what you see, if you zoom in, is that you've got this edge, this curve that's been broken into lots of bits of components. We're going to go further and we're going to insert what's called an inflation. Okay, so now this is going to essentially help us capture the behavior at the interface. So we're going to use the geometry of the total of all the face, and then we're going to use again our named selection, which is the inner edge. Okay, and then we're going to do 10 layers, 10, and we will decrease our growth rate to 1.1. So this will make each layer closer to it, because it's growing as it puts them stacks them on top of each other. Okay, so now if everything worked correctly, okay, you see there's no layered mesh here. If we generate it, okay, now you see that you have these nice layers to capture the behavior at this boundary. Okay. This is looking pretty good. We're going to go ahead and hit update, because this is faster than hitting close and then updating later. So you hit update, and it says it was successfully translated to Fluent, or to the workbench. Now we hit the close on the upper right. Thought I hit the close on the upper right. Okay, good. Okay, and now we're going to go into Fluent. So we double click on the setup. And in this case, so before we were just using single precision, okay, and so some of our residuals were good at like 0.003. We're now going to use, and we were only using one processor, we're now going to use double precision, and you can go ahead and up it to 4. Okay, so we're going to use a little bit more, it's going to be a little bit more resource intensive than it's been in the past. And we hit start. We're getting close. It's a little more detailed than what we did in COMSOL, but also it seems like there are a few more steps. Okay, and you can see that, you know, unlike with what we had at COMSOL, everything was in one software interface. Right, this is our 4th interface that we're using. Okay, so it's bringing everything in, hopefully, like we like. And this is the general tab that comes available. You see that we have the inlet and we have the outlet, so this is good. We are going to go ahead and we're going to look at the axisymmetric result. The model for now, we're going to do laminar, so I'm going to change it from SST, this turbulent model. I'm going to right click and then select the laminar model like that. Okay. And I can minimize this a little bit. For the materials, we're going to do this in water. Okay, that's what we were doing before, so we only have air, and we can right click and we can click new. And we can use the Fluent database, and we can go all the way down, and we can get water liquid, not water vapor. We can copy, we can close, we can look up here, and in the older versions, it would automatically put in water liquid, but for whatever reason, this is an improvement that you have to select water liquid. And we're going to change to create, and we're going to close. So now what we should have is a water liquid there, which we can then assign to the fluid zone, or fluid surface, like so. So we double click there over the left, and we hit water liquid. All right, we apply and close. Okay, so far, I'm feeling confident, but I do not know if this is going to work or not. Okay, so axis has been set up. That's the boundary condition. Inlet has been set up. Remember, we need to apply the 1 millimeter per second inlet velocity. So we come over here, and we go ahead and we can put in 0.001. Now, we might want to parameterize this inlet velocity. So if we want to do that, we can come and click on this arrow right here, and we can create a new input parameter. So if you are so excited about changing the inlet velocity, okay, from at the workbench level, you can do that. So now this is all set up. This is used as an input parameter, and we click OK. And we can apply and we can close, okay, like this. Internally, we should be all set. The outlet should be all set. Okay, the walls. So in this case, what we're going to say, the inner edge is really all set too. The inner edge is this one in the middle, okay, and that is where we have a no slip condition. So we can just close that. We don't have to do anything. The top boundary condition, right, this outer mirror, right, is where we're going to want to have no shear. So I'm going to double click on that one. And in this case, I'm going to be specifying the shear to be 0. So let's apply and close. All right. Let's see. In this case, if we look at the residuals, we're going to leave them as the defaults, all right? But it's still only at 0.001, but sometimes it's necessary to reduce those further. For the, and we should see now, we have a named expression of inlet velocity. We will eventually have another one for the drag force, but we're going to run the simulation first. We come over here, we click on initialize and calculate. Oh, I blast. Okay, so I hope I didn't just mess things up. For the initialization, we're going to actually use standard instead of the hybrid, and I'm going to put this back down to 0. Okay, all these things to 0. So I'm going to hit reset. Oops. Okay, well, I'm going to say they're 0, because that's what I think has worked in the past. Okay, I can click initialize. Okay, has not been saved. Okay, that's not a problem. And then we will go ahead and we will, I guess, initialize and calculate, not a big deal. Okay, so we're going to put those in place. But even doing something like that, running the initialization or running the simulation before I have the correct initialization scheme set up, as you know, could force me to do the whole thing over again. Good times. Let's see. We'll see how fortunate we get. All right, so now let's go ahead and let's take a look at the results. So we're going to make a new contour, and we can look at the velocity profile. We can call it velocity contour, like that. Then we can do save display, close, and that is disturbing, as we were suggesting. Okay, because what do we see there? Everything is 0. There's no velocity. Just want to make sure that we actually have an inlet velocity. Should be there. Okay. Oh, I know why it's not working. Haha, good. I know why. Okay, what I need to do is I need to increase the number of iterations. Right now it has 0 iterations. So you can put in 100 or you can put 1,000. It's really only going to use a couple. Okay, so here we go. We'll calculate. And now it's running. Okay, there we go. All right. All right, everybody. Okay, so you got to remember to do that stuff. Okay, to make sure you change the Oh, it's time. Time flies when you're having fun. Okay, I gotta just finish this thing for you. Okay. Okay, so we want to know the force. That was the big thing, right? So here we're going to calculate the force right here, and we're going to save it as an output parameter, and we're going to call it drag force. And just like that. So now that's there, and we're going to print, and we're going to take a look. Okay, and what do we see? We see that the total okay. So here it is. The inner drag force on the inner edge has come out to be 0.35 nanometers. That value is not what I would expect. It's not what you want to get either. It should be closer to 1 nanometer, okay? But we're going to have to be a little bit lenient because Ansys is doing funny things. Okay? If you come back out here, I just want to let you see a couple screenshots that will be helpful for you. We can close all this, and we're going to use this for future calculations. And you're going to be able to look at your design points. You click on the parameter set, okay? And you're going to put in different you're going to put in a whole bunch of different domain sizes, like 100, like that's actually too small, so maybe like 125, okay? Maybe 175, 200, 250, 300, 350, okay? You're going to put in a bunch of these sizes, and you're going to let it run, and you're going to end up looking for a plot. Okay, you would use something like this in MATLAB, okay? And you're going to look for the calculation of the drag force as a function of the domain height. So where would you say this is converging? There's not really a right answer. Okay, there's not one answer. This is where you have to judge. You may say here, which I say is wrong. Okay, so that's a wrong answer. Okay? You may say here. I say that's not the best answer because it's still doing stuff. But it does seem to stabilize, okay, out here. Okay, so either this point or this point or this point, one of those domain sizes would probably be appropriate. And this is how you would demonstrate your convergence for your demo simulation in your final project as well. And this is what you're going to do for the assignment. Okay? Here's the MATLAB code. You can take a look at it, and it'll be recorded. Okay, that allows you to do this pretty easily. What you do is you take the results from your table of design points, you're going to bring them into this Ansys _ data array, and then you're going to create these parameters and for the domain height and the drag force, and you're going to plot them, okay, as you see here. And then this is maybe a little bit more complicated, nicer plot of things as well, okay? And so this is going to be one of the things that you do. You're also going to turn on the turbulence. Okay, that's going to be something that you do. You remember you go back into Ansys and you change that turbulence, the type of flow that you have. Right now we put it in laminar, but you're going to change it to turbulent. And you're also going to eventually change the size of that ball to something that's greater than 1 centimeter. Okay? So there are going to be a number of things that you run with. But with what we've gone through, you should have enough to kind of struggle and get through the assignment. Any questions? All right. Thanks for coming. Yeah, okay. So we'll go ahead and we'll finish things up. I guess maybe I won't kill it. I might keep it and take a look at it for, I don't know, whatever. Let me stop the video.